Okay, so now you should have part one done. This n-gon row here is kind of confusing. I understand that. An n-gon is just saying that we have some polygon with n sides, and n is just a variable, so we don't really know how many sides an n-gon has, but it's a generalization. So what it's talking about is if we have, say, a 20-sided shape, a 20-gon, n would be 20, right? The number of sides of the polygon. If we had a 50-sided shape, we call it a 50-gon, right? Or so an n-gon, what we can think about is generalizing the patterns that we see in this table. So this really second column, the number of sides, is important to us because when we talk about polygons, we should know automatically the number of sides the polygon has. So if we talk about a hexagon, we should know it has 6 sides. So based off the number of sides, we want to generalize some of the patterns that we see here, okay? And then we're going to use Geogebra and look at really the important patterns, and that is the number of sides a polygon has and its angle sum that the polygon has, okay? So just so we can make some sense of this, this row or this column here, and I didn't get the title captured, but it's the same thing as your paper. This is the number of diagonals formed based off of the polygon with this many sides. And if you look at the patterns here, pentagon has 5 sides, we can make 2 diagonals. Hexagon, 6 sides, we can make 3 diagonals. 7 sides, 4 diagonals. And notice that the number of diagonals, if you look at the pattern, seems to be 3 less than the side value, right? So what we could say here is that based off of the number of sides, so we're generalizing a pattern here for the number of diagonals in terms of the side numbers. So in an n-gon, give me any polygon. I could tell you how many diagonals we can make based off of our one vertex technique, and all you do is take the number of sides the polygon has and subtract 3 from it, right? Dodecagon, 12 sides, subtract 3, we get 9. So if you give me an n-gon, where n's the number of sides, all I'm going to do is just take that number and subtract 3 from it, right? So that would be our expression for representing the number of diagonals that a polygon has, okay? Look at the number of triangles that we can make based off of the number of sides. Pentagon, 5 sides, we can make 3 triangles. Heptagon, we can make 5 triangles. Decagon, we can make 8 triangles. So it seems like if you give me the side number, all we have to do is subtract 2 from it, and we'll get the number of triangles made. So to generalize that number of triangles, we can just take the number of sides and subtract 2 from it, okay? And then we'll come back to this box here. This is really right here what we call the polygon angle sum theorem, okay? It's going to be our little rule that says given the number of sides n, we can actually write a little expression that will always find our polygon, or yeah, our angle sum of the polygon, okay? To actually make sense of this little box here before we get there, let's use Geogebra. And what we're going to do is look at our 2 quantities that are important to us here. The number of sides the polygon has, right? That's important for us. And the angle sums of the polygon. So we're going to take this column here and this column, and we're going to put them on a coordinate plane so that we can check out their relationship. Okay? So open up a Geogebra window and work along with me here. You can go side by side or pause this video, but open up your Geogebra window. Make sure that we can see our axes and we can see our grid lines here. Okay? If you don't see these options up here, again, remember, make sure that this little arrow is pointing down by just clicking on it, right? So, axes and grid line. Okay, we want to open up a spreadsheet, which is just the way that we can look at a spreadsheet in Geogebra is like an electronic table. Okay, so let's go up to View, and let's view our spreadsheet. So click Spreadsheet, and we get our spreadsheet to pop up here on the right. So this first column here is going to be, well, actually we have to determine, do we want our number of sides to be the first column or the angle sum to be the first column? So here's a big concept that we have to understand about coordinate planes and grids and why we want to graph. This x-axis is typically reserved for our independent variable. The y-axis is typically reserved for our dependent variable. Y typically depends on x. That's why we see y equals some expression in terms of x, right? So what we have to kind of think about is which variable here, the side number or the angle sum, which one depends on the other? So if you think about the way that questions kind of work, if I gave you a polygon name, you could figure out how many sides it has, and then based off of the number of sides that the polygon has, we could figure out the angle sum. So I hope that it makes sense to you that the angle sum values depend on how many sides the polygon has. Okay, so since I could pick any polygon and you can get its side number, like if I just threw out what's the interior angle sum of a 63 gon, right? A 63 sided shape. Because the 63 gon came out of nowhere, it's really what we call independent. It doesn't depend on anything. But since I gave you a 63 gon, we would need to know the side number so we could figure out the angle sum. So the angle sum actually depends on the number of sides the polygon has. So keeping that in mind, we're going to use this first column in our table to be our independent variable. So in this first cell, A1, I'm just going to title this column N. N is going to stand for the number of sides of the polygon. And I'm going to fill out this column here and fill this out with me too so it matches our table. So we have a triangle with 3 sides, quadrilateral, pentagon, hexagon, heptagon, octagon. We actually skip the nonagon, the 9-sided shape, and the table goes right to decagon, 10 sides. It skips an 11gon and goes right to a 12-sided dodecagon. Okay, so the number of sides, I'm just matching our table that we have here. Okay, and we'll get to the N later. All right, now the next column here, which will be our other quantity that we want to check out, the relationship between the number of sides and the angle sum. Maybe I'll call this, I'm going to call this S for sum. Okay, so this will be our sum column. So in a triangle, we have 180 degrees, quadrilateral 360, pentagon's angle sum was 540, hexagon angle sum was 720. Heptagon, I think, is 900. Octagon is 1080. We skip the 9 side, and the decagon, I believe, has 1440, 1440 as an angle sum, and the dodecagon has an angle sum of 1800. So there's our information based off of the table here, right? I took the number of sides and the angle sum. So now we have this electronic table here. So let's go ahead and plot the points here. We'll let the x-axis be the number of sides the polygon has. The y-axis is going to be the angle sum. So just click in this cell A2 where our 3 is, in the shaded region in the cell here, and just drag so that we can highlight all of our data here. Okay, once you get that done, notice our tools up in Geogebra change. Okay, so we're going to grab in this third toolbox where it's this green 1, 2, which is a create list tool. Hit the little red arrow so we can drop down the tool box, and then click on create list of points. Okay, so create list of points. We get this little window to pop up. The name of it is list 1, but more importantly in the preview you can see our list of data points, 3, 180. So 3 sides, 180 degree angle sum. 4 sides, 360 degree angle sum, and so forth. So that looks great, and hit create. So what you get right now is in our algebra window we get all the points that we just made, and there should be a point for every data point that we have over here in the spreadsheet. But nothing comes up here in our algebra window. Okay, and actually I'm going to hide the spreadsheet. We're done with the spreadsheet right now because we did create our list of points from our table. Okay, so now if you look at our x-axis, we have our number of sides, really 3 for a triangle, up to dodecagon 12, and we have some more, and that's good. But we have to get to our lowest angle sum, which is 180. Okay, so to do that, what I want us to do is grab your Move Graphics tool, put your pen right on top of the y-axis, and drag your y-axis towards your origin. So drag it down. Notice that's changing our scale. And hey, our points just came into view, right? So we have our points right now. If you drag your y-axis down, we can see our points here. Here's 3 180, 4 360, 5 540, okay, and so forth. All right, so here's our data, and the beauty of a graph now is we can see the relationship between the number of sides a polygon has and the angle sum, and it looks like a nice linear pattern, right? So what linear means, again, is that as we increase a side length by 1, we increase our angle sum by 180 degrees, right? That's our pattern based off of the table here. So as we increase this again by 1, we go up by 180 degrees. Increase by 1, go up by 180 degrees. So as we increase our side length by 1, we just add 180 degrees, right? And notice as we go from this point F, which is an 8-sided shape, an octagon, we are missing our 9-sided shape, right? We never put that in our pattern here. But if we knew that point, then we can get to the next one, and the next one, and so forth, right? So this is a nice linear pattern here. So now what we want to be able to do is let's create the line, if this is linear, the line that goes through all these points, which we're going to call our trend line. Okay, so we need to come up with the equation of a line that fits all these data points. All right, and this equation that we're going to come up with is our polygon angle sum theorem. Okay, so let's go back to this idea here. Let's reason with the sum of a 15-gon. Okay, so I'm going to grab this 15-gon tool here. All right, whoops. So here's a 15-gon. With smart software, I can just make one. So what we need to do is, if we want to find this angle sum, and this is what we did to fill out our table, grab a vertex, see how many diagonals we can make, right? Here's 1, here's 2, here's 3, here's 4. You know what? I don't want to do all that, right? So let's look at the pattern of our diagonals, actually. So if you give me the side number, like a 15-gon, didn't we say before that you could just subtract, looks like 3 from the side number to get the number of diagonals? So 15-gon, if you subtract 3, we're going to get 12 diagonals, right? And that's based off of our table here. Now that we have our diagonals, we want to count how many triangles we can make. But we already talked about that pattern too. If you have the side number, we can just subtract 2 from the side number, and that'll be the number of triangles that we can make. So in our 15-gon, we would just subtract 2 from the number of sides, right? 15 minus 2 is just 13. So really, if I were to continue out this pattern, we would make 13 triangles. Sorry, that's an ugly 13. But knowing that there's 13 triangles and each triangle has an angle sum of 180, we could just take 13 times 180, and that will actually give us the angle sum of a 15-gon, right? And so if we check that real quick, what is the angle sum of a 15-gon? So if we take 13 times 180, we get an angle sum of 2,340, okay? So let's check that in Geogebra, 2,340. So I'm going to put that point, click in your input bar back in Geogebra. In our input bar down here, we're actually going to put the ordered pair. So I'm going to hit Shift 9 to start my parentheses. Geogebra knows that once you create a left parenthesis, it knows you need a right one, so it'll automatically give that for you. But we're going to have the ordered pair 15, that's the number of sides, and our angle sum 2,340. And if you hit enter, notice that point that pops up fits our line nicely, okay? All right, let's write this rule here. So what it seems like we have to do is figure out, given the number of sides, we need to find out how many triangles we can make in the polygon, which is just the number of sides minus 2, right? And I'm going to put that quantity in parentheses. And then we're going to take that number. This is just our number of triangles, right, that we can make. So 15 gone makes 13 triangles. And then we just take that number of triangles times 180 degrees, okay? Now, we're human, and we know that n stands for the number of sides, but Geogebra is a computer program, and it only really knows what x and y are. So instead of saying n, the only difference is going to be, I'm going to call our number of sides x, because that's what Geogebra knows as a variable. So instead of n minus 2, we're going to say x minus 2. So in your input bar, I'm going to do parentheses again, and I'm going to say x minus 2. In that parenthesis is going to represent the number of triangles that we can make, and then we take that times 180 degrees, which is our angle sum for a triangle. So you have the number of triangles, x minus 2, times 180. So let's hit enter, and nice, we get this good line that goes through our data. Okay? The last thing that I want to talk about with this, now that we have our rule written, this is now our polygon angle sum. You give me a side number, I'm going to just subtract 2 from it. That gives me the number of triangles that I can make. Then I'm just going to take that times 180, and that'll always give us the angle sum of a polygon. So let's check this real quick. Notice we don't have, say, the 11 gone here. We missed that in our table. So the easiest way, without us actually even crunching anything, when we put an expression like our x minus 2 times 180 in our input bar, it creates a function, and you can see that up here in our algebra window. It's called f, right? Our function f. So all that we have to do is, I'm going to use my pen tool to show you what we're going to type in our input bar. So if I want to find out the angle sum of 11 gone, what I'm going to do is put the point, so I'm going to use a parenthesis, 11, that's the number of sides, that's our independent variable, and then I'm going to say comma f of, and then in our f function I'm going to put in 11. Okay, so we're evaluating our f function with 11 sides, right? So this is what we're going to type in our input bar. So in my input, I'm going to hit left parenthesis, I'm going to say 11 comma f of, so the parentheses, 11. And notice Geogebra does those two right parentheses for us, so we're good. So we should have your ordered pair look like this in the input bar, and hit enter. And now our new point pops up in our table, and in our algebra window it tells us the 11 side, and look at this next number here, 1620. That is our angle sum. So that's the beauty of Geogebra and the beauty of functions. If you know the function, like our rule that we have up here, then all we have to do is just do whatever side number we want to put in, f of that side number. Okay? Let's try one more, and then you can do a little exploring on this. I'm curious what a 50-sided shape, what its interior angle sum would be on a 50-sided shape. So all we're going to do in our input bar is exactly what we did for 11, but instead of 11 we're going to say 50, right? So we'll do an ordered pair, and we'll say 50 is the number of sides, comma, f of 50, right? So f parentheses 50, like that. And then if you hit enter, even though we don't see it on our window up here, because 50 is way out here to the right, and the sum is way, a lot bigger than 2200 that I'm looking at, you can see in our algebra window it created that point for us. So a 50 gon actually has an angle sum of 8,640. So this now that we know the pattern of our angle sum, we wrote the rule for give me any angle or any polygon side number, and we can crunch its angle sum very easily, and we don't even have to do any work. We can let Geogebra do the work for us. Okay, so play around with that, guys, and answer the questions of this quest, and you can use this app now to help us or help you verify your answer. Okay, so I hope that made sense. If you have any questions, please, guys, ask me. Thank you.